يعطيكم العافية جميعا. اليوم حنكمل بإكزامبل نمبر 2 ضمن chapter 1 serviceability limit state design. طبعا نحن بلشنا حكينا last week بموضوع deflection, how to determine deflections for beams, reinforced concrete beams, considering whether beams are lying in cracking zone or uncracked zone. So today's example, we have a reinforced concrete beam as shown in figure 1. The beam is cantilever beam and is subjected to two loads. A uniformly distributed dead load of 15 kilonewtons per meter. When we say total dead load, this means the summation of the self weight and the superimposed dead load. So no need here to determine self weight. This is the total dead load. And we have a concentrated live load at the beam step, which is equal to 60 kilonewtons. The concrete used is normal weight concrete. The compressive strength is equal to 28 MPa. As we see here in figure 2, the beam is doubly reinforced section. It's not singly reinforced section, which means that we have reinforcement in the compression zone. It's reinforced with 6 phi 29 millimeters in the tension zone, and in the compression zone we have 3 25 millimeters rebars. The beam has dimensions of 500 millimeters versus 900 millimeters as a depth. The cover to the center, we have here 100 millimeters for the top reinforcement and 60 millimeters for the bottom reinforcement. It's required to determine the short-term deflection at the beam step. So we all know that the short-term deflection is equal to the deflection due to dead and live minus deflection due to dead only. So we need to determine delta dead plus live, and then to determine delta dead, and then we subtract these two terms to determine delta short term. Here we are going to use a modular ratio n, which is the ratio between the elasticity modulus of steel to the elasticity modulus of concrete, n will be equal here to 8. So first of all, we start checking the minimum depth required as per ACI requirements. H minimum for cantilever is equal to L over 8, which is 5,000 millimeters over 8, yani 625 millimeters, which is less than the actual depth of the beam, which is 900, which is okay. In case this number was greater than 900, we need to increase the depth because we know that we could face deflection problems in the future in case we didn't stick to this limit. Now let's start to determine delta dead. First of all, we need to find the dead load moment. We have uniformly distributed load, so we have cantilever beam. The rule is WL square over 2. W is 15, L square is 5 square over 2, so the dead load moment is equal to 187.5 kilonewtons meter. The rupture modulus, Fr, which is 0.625 radical F prime C. F prime C here is 28, which is the compressive strength at 28 days. Applying this equation leads to F rupture equal to 3.31 MPa. Please pay attention for the units. I gross, which is the gross moment of inertia without considering steel reinforcement effect. Here we have rectangular section and the inertia is calculated about x-axis here. So the rule is 1 over 12 BH cube. BH is 500, H is 900. So the rule is 1 over 12, 500 times 900 cube. And this is the answer, 3.04 times 10 to the power 10. Now, by knowing Fr and I gross, I can determine M crack because it's very important. This is the limit where I can say whether the beam is behaving as a cracked section or uncracked section. So M cracked is equal to F rupture times I gross over YT. YT is the distance between the neutral axis of the uncracked section till the surface of where the beam is under tension. In our case, it is the top surface of the beam, and the distance is from the center to the top surface, which is half the beam's depth in the case of rectangular sections. So it's 450. The YT is 450. So M cracked is equal F rupture I gross over YT. Direct substitution, M cracked is equal to 221.6 kilonewtons meter. Now, since we are dealing with ACI 318 2019 edition, the new code says that we have to take 2/3 this value. So we have to compare M dead with 2/3 the M cracked. In 2014 version, no, we used to use only M cracked. So M dead is equal to 187.5. 2/3 M cracked is equal to 147.7. So here it's greater than the limit stated by the code, and therefore the section is cracked. That's why I need to determine I effective. We're going to follow this chart as mentioned the last week in order to save time. N is given as 8. Now we will deal with the second case, by the way. In the first example last week, we solved the example using the first case. It was a single reinforced section. In today's example, the beam is doubly reinforced section. So I'm going to use the second shape. But there are some common factors which are N, B capital, and I gross. Let's see, N is equal to 8. B capital, as the last time, is equal to B small, the beam's width, divided by NAS. Beam's width is 500 in our case, millimeters. N is 8. AS, we have 6 29 millimeters rebars in the tension zone. So it's 6 times 645. 645 is the area of one 29 millimeter diameter rebar. This is the value of B capital. Then we have to determine another factor, which is R small. It's N minus 1 AS prime over NAS. N minus 1 is 7, since N is 8. AS prime is the area of compression steel. We have 3 rebars, each has an area of 509, divided by NAS. N is 8, and AS, the total AS, we have 6 29 millimeters rebars. So 6 times 645. The final answer is equal to 0.345. Now, by knowing B capital and R, we can determine KD. So last time KD was determined from this equation. This is for this without compression steel, for single reinforced section. Now we are going to determine KD, which is X, as we go to in RC1, the neutral axis depth after cracking, which is the same as KD. KD here is going to be determined from this equation. So we'll write down the equation here. It's 2D B capital 1 plus RD prime over D plus 1 plus R all square, all under square root, minus 1 plus R all divided by D. D prime is the distance from the compression surface to the center of compression steel, which is 60 in our case, okay? Whereas D is 900 minus 100, so it's 800. We know these terms from RC1, just to remind you. So KD, by applying this equation, will be equal to 246.5 millimeters. Then we can go to determine I cracked from this equation. Also, it's in terms of B small, which is 500. KD, we already determined it, 246.5. D, the effective depth, it's 800. N is 8. AS is the total tension reinforcement, which is 6 times 645. AS prime is 3 times 509. D prime is 60. Direct application for this rule, we can determine I crack, which is equal to 1.25 times 10 to the power 10. Always, always, always I crack must be less than I gross. So if I checked I gross, let's see here, I gross is equal to 3.04. I cracked is equal to 1.24. Okay, this is just take a quick check. Now we can go and determine I effective. This rule is taken from the ACI code also, 2019 version. I effective is equal to I cracked over 1 minus, we open a bracket, 2/3 M cracked over M applied. M applied in our case is M dead load, all square times 1 minus I cracked over I gross. Direct application, we have I cracked, we have 2/3 M cracked. The M applied here is M dead load. We have I cracked, we have I gross, so I effective is equal to 1.96 times 10 to the power 10. Now we can determine delta dead. طبعا there is an equation for cantilever beam subjected to distributed load. The deflection at the tip is equal to, in this case, W dead, the distributed load, times L to the power 4, which is the span to the power 4, divided by 8 EI. E is 4,700 radical F prime C, these two terms. I is I effective. L is the span. W is 15, the distributed load. طبعا it's worth it to mention that 15 kilonewtons per meter is same as 15 Newton per millimeter. That's why we didn't change anything. So delta dead is equal to 2.4 millimeters, which is the deflection due to dead load effect only. Now we need to determine the deflection due to dead plus live load, and then we subtract both terms. Now we are going to repeat the same steps, but we need to determine M live. And since the live load is a concentrated load and not a distributed load, we have different equation to determine it. M live here is equal to load times distance. Since if we go back to the example, this is the live load. The moment here is equal to PL times 5. PL 60, the span is 5. 60 times 5 means the moment due to live load is equal to 300. So going back to the example, 60 times 5 is equal to 300. Then M dead plus live, we add the dead load to the live load. This is the total, 487.5. Definitely it will be greater than 2/3 M crack, since the dead load itself was greater than 2/3 M crack. What about the combination of dead plus live? So that's logic. So it's gonna be a cracked section, so we have to determine I effective. So I cracked was determined earlier as 1.24 times 10 to the power 10. We do not have to determine it again. We determine it once in rectangular section beams. So now we substitute with the same equation to determine the new I effective. I'm just going to change the value of MA to replace it. Instead of putting the value of dead load, we are going to use the value of moment due to dead plus live. This is the only change actually. Therefore, the new I effective due to dead plus live is equal to 1.31 times 10 to the power 10. Now, to determine delta dead plus live, here we have two different load, let's say, types. One uniform distributed load due to dead, and it has its own equation, which is WL to the power 4 over 8 EI, plus the other load due to live load, the other deflection equation, which is PL cube over 3 EI. So we add the term for dead load plus the term for the live load. Here we add W L to the power. This is the same as this one, but with different I effective, because we are going to use the new I effective due to dead plus live, plus P 60,000 newtons, not 60 kilonewtons, times L to the power 3 over 3 EI. This is the new I. The summation will give me the total deflection to dead plus live. Now I already know the deflection due to dead plus live, the deflection due to dead only. We can determine the short-term reflection, which is delta dead plus live minus delta dead, and in our case it will be equal to 8.87 millimeters. That's it for the day. I hope that the example was clear. In case you have any questions, please do not hesitate to contact me via my BAU email. Stay safe, study well. Wassalamu alaikum.